Hello again and welcome to RP-0 America. So this will be our first launch using a Saturn V. I've got myself aligned with the moon already. I just had gone set target and using relative inclination, which I set up my MechJeb window to show. I just want to get that kind of close as I can to 0 degrees, which half a degree is pretty close to it. Alright, so let us take off, and I can talk about the payload and the launcher a little bit. We have an uncrewed craft, so basically the same payload that I was testing before on a smaller rocket, the Saturn V. And engines up to thrust. Alright. There we go. So we're off the pad. Pretty low thrust-weight ratio, but that's just sort of the standard for a Saturn V. So the Gemini-Direct payload with all full tanks and everything is about 30 tons, which is at the really low estimate range of what a Gemini-Direct craft would take. So it kind of has optimistic mass assumptions in how it's built and kind of configured. But yeah, 30 tons is well within the range of what a Saturn V can throw towards the moon. It threw about 50 tons towards the moon in the Apollo command and service module and lunar module. About 30 tons for one, 20 tons for the other. Total payload of about 50 tons. So this payload can definitely be thrown pretty handily towards the moon by a Saturn V, which is nice. So this will be our first test of of the fully loaded payload as well as of this launcher at all. The Saturn V engines underwent a great deal of ground testing, and so they're really reliable. So at this point, test flight doesn't really play a part. It's just about me actually carrying out the mission successfully, which for missions where you go beyond just low Earth orbit, a week or two up there, I find just the challenge of carrying out your mission correctly is hard enough. All right. So with the stages, the first stage, second stage, and a bit of the fuel of the third stage will be used to park our final payload in low Earth orbit, and remaining fuel of the Saturn, the S4B stage, will be used to throw our payload towards the moon. Let's see. Just want to try to get as much into each video of this as I can. It says this will be the one uncrewed test of these, and so in throwing the payload towards the moon, we can test out these stages in their kind of actual desired usage case scenario. Basically in the vicinity of the moon and potentially towards trying to land this uncrewed capsule on the moon, for all we know. I'm not sure how successful it'll be or not. I haven't tested this in quite a while, in a month or two, since I originally kind of quickly tested it out once I got this payload from Schaub's. All right, so pitching down. Probably want to pitch down just a little more. Saturn V isn't too difficult to fly, despite what you may think, because it's such a huge, such a heavy lift vehicle. Do I have this on? Yeah, there we go. Let's make it just a little bit brighter, make it a little easier to see in video. You just kind of have to be careful. I don't know. You basically treat it like any other rocket with the same thrust-weight ratios as this one has. Just think about it like you're steering an elephant. It's not particularly nimble. So you'll probably want to do a couple practice runs before launching any Saturn V's for real. But we're past maximum dynamic pressure, almost 2 minutes into the stage. So the Saturn V is really, really interesting vehicle. I just film videos talking about it, and documentaries. Many documentaries and books have been made on it. So I'll just cover its kind of flight profile information a bit. So it starts with these 5 kerosene and liquid oxygen fueled engines on this huge first stage, and partway through ascent. Let's pitch down even a little bit more, not exactly towards the horizon. So I do want to keep this number down as low as I can, the relative inclination. All right, let's just go to prograde now. So partway through ascent, when G-forces were starting to get high, there's a number of reasons you want to keep the G-forces of your rocket limited. So for just pure delta V efficiency, you could leave all 5 engines on, but in practice, to reduce stress on the rocket, reduce stress on certain rocket components and the crew, the center engine was shut off. There we go. I just shut it off. I had a hotkey set for that, so that brought down the g-forces of this. So the peak acceleration that this rocket has to experience during ascent is reduced by about 1/5 by cutting out that center engine early, which is less stress on the crew. It's less, what do they call it? Well, less pogo is kind of the outcome of having the rocket's superstructure, and fueling system experiencing a wider range of g-forces. But there's, what is it called? It's compression. So basically you're pushing the rocket from, imagine it's being pushed from the bottom, and as it's experiencing a larger and larger acceleration, it kind of, think about how you would experience g-forces if you tried to stand up, even under 3.5 G's. Like, you're going to have compression down your spine, and that happens with the rocket structure too. The steel has to, the superstructure has to withstand this acceleration, and so it kind of compresses it, and then boom, once that stage burns out, it springs back because it's no longer experiencing that. Darn, I saw this happen before, but I'll just ignore it because the rocket itself looks cool enough. So we've dropped the stage, so we fall into 0G. So this whole superstructure, which was compressed by that acceleration, just all of a sudden springs, and so fuel will be pushed off. You will just kind of be flung off the bottom of the tank. It's hard in general on the structure, so we need to ullage the fuel to settle it back towards the pumps. It has a set of solid rocket engines which burn, settle the fuel, keep them going to the pump while the engines build up thrust. And there we go. Once that's complete, this is it's called dual plane separation. There we go. So whatever crazy effect was going on is kicking out. I imagine it's a scatterer effect that caused it to go dim between 100 kilometers and 130 or 140 or something. And that's really nice. Really cool it threw the ring off like that. I always love when the thrust will hit the ring. That's realistically something that happened where the ring was obviously affected by the thrust of these engines, and it's really cool to see it actually occur and kind of fling it off in a non-predictable fashion like that, where it kind of spins or something weird. Alright, so I'll just keep an eye on this relative inclination to reduce it. I haven't been purposely doing that, but thankfully it did start to come down. So now this stage, it has 5 also very large engines, but about 1/5 of the thrust, or something on that order, 1/5, 1/6, something like that, compared to the first stage. Much more efficient. So it's a much lighter stage because this fuel is liquid hydrogen, liquid oxygen, which is also what contributes to that raised efficiency. Let me change the camera to free now, and just kind of pitch it just a little bit so we can see America. Alright, so I want to keep an eye on this. So they're very high efficiency engines, but they're lower thrust. So at the beginning of this, unlike at launch, the first stage has to produce a thrust weight ratio of over 1, obviously, and it produces a thrust weight ratio of 1.15 or so in the Saturn V at launch. It can get away with having a wider range, because if you had higher thrust engines, those would be heavier engines, which would mean the dry mass of the stage would be higher, so the total second stage would actually end up producing less delta V, because a smaller fraction of this stage's mass would be fuel. Instead, more of it would be structure to withstand the acceleration and engines to produce that thrust. So these engines can go through a much wider range of g-forces of the overall vehicle than you could with the first stage, because you don't have to be over 1 G of thrust-to-weight ratio with a second or a third stage. Even some modern rocket upper stages have a ridiculously low thrust-to-weight ratio for the upper stage, which is like 0.6 Gs, which takes that burns for like a total of 15 minutes or so, and barely kind of approaches 1 G, and that's just to keep the dry mass down. So a larger portion of that stage can be fuel instead of engine and tank, which allows it to deliver more delta V, which lets you do more with the payload. So these are really high efficiency engines, but these J2 engines they can't push as hard against the atmosphere, which is why that whole first stage is used to kind of push this. This is still in a, we still have most of the fuel left, but it is such a huge second stage and third stage and payload. Just to throw this amount of huge rocket above the atmosphere so these engines can actually reach the great efficiencies that they can. And huge thrust for a liquid hydrogen engine at this time. These are astounding amount of thrust for an engine. The only liquid hydrogen, liquid oxygen burning engines that the US had before this were the RL-10s, which produced 60 to 100 kilonewtons of thrust versus 1,000 that you see in this, with about the same efficiency. Obviously, more modern engines have higher efficiency, but this was kind of a crash program to demonstrate: can we burn liquid hydrogen? Yes, we can. Can we burn it in to produce a substantial amount of thrust like the RL-10 could, and then finally to produce a huge amount of thrust like the J2 engine does. And not only that, the J2 engine actually is able to restart in space, without ground control, without additional human or ground equipment intervention. These engines are able to restart themselves in flight. Just an amazing amount of development of that technology was required and carried out for the Apollo program. So we are approaching our apoapsis. I don't have to be too careful about this flight profile, so I wouldn't. I've done other videos, and other people have done other videos of an ideal flight profile for a Saturn V. So that's not what I'm aiming for here, because I don't have to throw very much mass at the moon in this case at all. 30 tons versus the capacity of this rocket would be to throw about 50 tons. So even though in-game the actual mass of this payload is about 30 tons, realistically, in my opinion, an actual Gemini-Direct would have been closer towards 50 tons, certainly under 50 tons. They could have done a two-crew direct mission with a Saturn V. Just in my case here, with this actual payload as constructed, it's a bit lighter than much lighter than the Saturn V's limitations. So I don't have to be too cautious with how I fly it. All right, so that's the rocket, first stage, second stage. The whole Saturn V is just an amazing feat of engineering. Done in a very short period of time, very reliable as a flight-ready rocket. I'm pretty sure they flew 2 of them at least uncrewed. They set up a contract to make the technology, and NASA, a contract to get a certain number of Saturn V's. So they had a kind of a long lead time where they knew how many they'd have, so they kind of had to figure out what to do with them. So they did a couple of uncrewed actual flight tests to confirm and demonstrate that everything worked. And obviously they learned some things during those uncrewed flights, like pogo, which caused some damage to fuel elements, researching and doing nuclear things, not fuel elements, to elements of the fueling system, caused engines to shut down prematurely because their fuel lines were damaged. Let's see. Just pitch up a bit. I want to manage this vertical speed, and I'm doing that by pitching up, because this acceleration increases, which is providing more and more velocity change per second, obviously. But I also want to emphasize some of that velocity change to counter our current fall, because by the time this stage burns out, in 2.5 minutes and change, we want to be traveling in level flight, so not falling, not rising. We want this to be around 0. So 2.5. Let's go to 30. Just to keep it going. So they learned a lot from those uncrewed test flights, and then they had to be kind of strategic about the use of the remaining Saturn V's to be able to kind of demonstrate all the hardware, let people fly with it to test it out. And there was a limited amount of rockets and time and automation at the time, so I don't think they did an uncrewed mission similar to what I'm doing now, where they sent the whole payload towards the moon with no crew. But that's okay. I mean, I'm also using Gemini-Direct and not Apollo. and they had some test articles left of the Saturn V, which is what you'll see at museums now. In developing, they developed the technology, like the engines for the Saturn V, and as well as the manufacturing techniques to make those engines and to make the tankage kind of to the quality and kind of mass requirements they needed to actually use it on missions to the moon. And so they made test versions to kind of test out the fabrication equipment. So they actually had something. So let's say the team who's working on this second stage would kind of develop a test article that other people who were working on, say, the first stage or the third stage could actually see and NASA could they could interact with and test to see how it would actually end up working with their components. So it was a very complex project management, but there are some physical examples of the Saturn V still around. You can see it at, I think is it just 2 museums? I know there are places I can't really go, in Florida and is it Alabama? Oh, I can't remember. It's somewhere kind of on the Gulf of Mexico, because the first and second stage of this, like you saw their masses, but they're, what is it? Is it 10 meters across? And so they're so large, you can't really ship them by road, you can't really ship them by rail. They're too big to put in an airplane, so they moved the first and second stages via barge from where they were manufactured on the Gulf of Mexico in a southern state, over by barge around Florida to the launch complex. All right, let's pitch down just a little more. Now this is starting to level off much more comfortably. We can just manage this pitch to level out as our to stop influencing this vertical speed as it approaches 0. So if you recall how much delta V it takes to get into orbit, we're not going to have enough in the second stage alone to reach orbit, which is, again, fair as a previous, similar to what I said in the previous video. If that were so, the dry mass of the second stage would also be part of what had to be put into orbit. So it would take a lot more fuel and energy to place this whole giant dry second stage into orbit, whereas here, because it's suborbital, you've kind of wasted less energy putting it into, you don't have to put it in orbit, you just kind of bring it into a relatively high suborbital trajectory. So another thing, as you can see, so we're now at pretty high g-forces. So those astronauts had to experience a pretty wide range of g-forces in the first stage, pretty wide. No astronauts in this current flight, but the craft and future astronauts will experience a very wide range of g-forces in the first and second stage. And for similar reasons, they cut off one of the center second stage engine a little early before stage burnout to limit the chance of pogo, to limit the range of g-forces that the crew and craft would end up experiencing. And it just gives them a little more leeway, because if they had any kind of trouble, let's say a little more residual fuel in the first stage didn't burn, or the trajectory was just a little bad, they'd have a bit of flexibility of to cut off the center engine a little early or a little late and adjust the trajectory to account for things that happened during previous sessions of the flight. Oh, I've lost my relative inclination information. Oh, and that stage burned out. So we're jettisoning the second stage. So if you take a look at the change we saw in the dry mass, that's how much mass was in that. And then we ullage. So a couple of solids burned. I'm pretty sure those were weird. There's in FASA, they don't actually exist, but they're kind of separated solid rockets that were attached to this, and then they would burn to kind of stabilize the fuel of this, and then they'd be thrown off. Whereas I put 4 tiny nozzles in here to basically do that, to ullage the fuel. Even though in practice, just because I light the engine fairly quickly, I don't need it from the way that Real Fuels is pretty flexible. It's pretty forgiving right now in how long it takes for the fuel to destabilize, where you actually will need to ullage it, but I still put all the necessary systems on anyway. So for the full Saturn V, they did have a couple of small solids to ullage this third stage before ignition, and as you can see, they tested between 2 and I think maybe up to 6 or 8 of these little APS flight packs, which are liquid hypergolic packs, which were used to provide the ullage for the later burn. so let me just select the moon again. Ooh, we're 2.7 degrees off. Oh boy. All right. So I probably can't correct all of that. And we're wandering even more. So let me just do this by hand to quickly figure out where... Ooh, okay, that's putting me off even more. I guess I can see because of where the purple dot is, eh? Probably should follow it. All right, let's go this way. So I want to decrease that as much as I can. And thankfully I have tons of extra fuel. So realistically, they would not have... this is an exaggeration of what they would have potentially done to fine-tune various flight parameters on the way to orbit. So I'll pitch up just a little bit because I definitely want this to level off to 0. So yeah, this doesn't need to be 0, but it just makes it a lot easier to hit the path of the moon, because if your craft is right aligned with the orbital path of the moon, it just makes it a heck of a lot easier to intercept it. Basically, anywhere you travel in the moon's path, you will be aligned to it, rather than kind of having to make sure you cross over the moon's path just at the right point in the moon's path. Probably not doing a good job of explaining it verbally, but it's just a difference where if you set up your conditions right, you kind of reduce a 3-dimensional problem to a 2-dimensional problem. Oh, so now we're pitching up enough. We can pitch down a little more. Yeah, it looks like it's going all right. So I can correct that in flight as well later on. Time to AP. Okay, so we are approaching orbit, because this time, even though we're pitched pretty low, just 8 degrees and now falling, this time to AP is still not falling. So let's just pitch down just a little more. Oh, come on. Oh, I see, I had SAS on, so it was kind of correcting my corrections. And I am now technically pitched down just a hair less than a degree. And this is accurate for how long it would take for the whole Saturn V to burn its way to orbit. Some rockets, like the Titan II with the Gemini you saw in previous videos and in history, they took like 5 minutes to get to orbit because the thrust-to-weight ratio of the engines was just so high, whereas this takes on the order of 15 minutes to get to orbit. The slow road to space. Okay, so we are approaching orbit. As this approaches 0, and then we'll flip to positive, and then I will shut off the engines. Getting there, looking good. So we're heading down just a hair now, which is okay. Technically we are pitched up just slightly. And relative inclination is now actually traveling the wrong way. It hit its minima of 0.78 or something like that. So can't see multiple things at once. There we go. All right, so that looks good enough to me. And all right, so seems good enough. All right, so we are now in orbit. So this is a pretty low orbit, way below the orbit, say the International Space Station would be in, for example. And just because this is going to be where it is for a very short period of time. So let's just lock it, give it the RCS so it kind of will correct itself to stop it from wobbling in its orbit as much. All right, so let's see. So I like to use MechJeb to set this up, but in practice the moon is there. If you like to do it manually, which is a great way to to learn these things. Oh, come on, it's freezing up a little bit on me there. All right, so you can see the moon. So we would want to do a burn somewhere over here and just stretch it out, etc. And that would kind of, and then you can go about adjusting this to, sure, why not? I'll do a vague one, and if I can't get it perfect enough, I'll just let MechJeb give me a quick perfect one. But MechJeb has a way to do this as well. You just set it up to encounter the moon. Tell it to give you as close of an encounter to the moon. All right, so it's telling me that by the time I come out here, the moon's still going to be over there. Okay, so that's telling me that I want to drag this over here. All right, and it's starting to tell me encounter information, so let's just align it nicely. So this is pretty much where I am. So it's going to be about 1 full orbit around before my first opportunity to do a burn towards the moon. So I'm going to see, this is where it's a little rough, like the fact that it's kind of gives me a weird swing there. So this will probably be the, to some people who are just kind of watching this as entertainment, this will, oh crap, will be the boring part of the video where Kyle just drags around delta V. But to people actually trying to figure out how to do this on their own, or kind of who want to know how and why I'm doing weird, random different things, this will be the dialogue where I explain what I'm doing, why I'm doing it. Right, so first I'll just kind of get it vaguely in the ballpark where I can see the encounter. Oh, geez. I'm there. So, kind of dragging this by hand, I always find it frustrating because I'm a little ham-handed. So, once I'm to that point, I'll use Maneuver Node Editor, which is very nice, and I will focus on the moon. So that'll change kind of the perspective of the flyby it's showing me. So here I can kind of optimize it because I want a close flyby, because I'm going to modify that with some of my later stage fuel to turn into an orbit. All right, so this gives me an opportunity where I can shift time. Nice, that you can tell that I was shifting by like hundreds of thousands of seconds for a burn of a Jupiter mission. Whereas here I don't want to adjust my burn. So this is adjusting when the burn happens rather than dragging it around physically. I just find it so much nicer to just click like so. So I'd ideally like to end up kind of equatorial, like in the same plane as the moon is, so that going back to Earth is easy. But that's not a pure requirement, because I might be going beyond just getting into lunar orbit and then breaking lunar orbit and coming back to Earth. I might actually be landing this craft. We will see how well it performs in an upcoming video. So, all right, decrease my delta V just a little bit. So see, like I could fine-tune these, or I can fine-tune this time, let's say by 3-second bits. Or I could also set up a burn mid-course. So in this video I won't be showing how to set up a free return trajectory, because that's a little more time than I have left in this video. I'm pretty sure I've done that. I've shown that in at least one other video, because and Nathan Kell has done it. So free return is really cool. It's where you basically the burn I'm planning up to do, where you leave low Earth orbit and head towards the moon. You'll slingshot by the moon such that the influence the moon's gravity has on your craft will bring you back in close vicinity to the Earth. So in case anything went weird with your craft, and you didn't think you didn't rely on it to put you in a lunar orbit or carry out the rest of your mission, you could just do nothing. Just don't assume engines will work or anything. Just don't light them up, and that will result in the moon's gravity carrying you back safely towards the Earth. And as long as your other final systems will work, if you believe you can rely on them, then you can just return safely to the surface of the Earth. Apollo 13, of course, had a failure shortly after they left their free return trajectory, because any Apollo mission towards the moon would first do their first burn leaving Earth, and then final tweak corrections so that they were in a free return trajectory to Earth, and then partway to the moon, a day or two into flight, they would either make fine-tune adjustments so that to make it so they get a closer path to the moon. Like here, we're going to go within 260 kilometers of the moon, which is pretty close, as you can see, kind of how it's skimming. And you can obviously skim a little closer. I could skim a little closer by doing a tiny mid-course correction, which I'll probably end up doing, possibly on video. But this is as close as I'm going to end up getting now. So they would do a mid-course correction to go from a free return trajectory to something like this, where you're going to get a close skim of the moon, so that at that close approach, actually I can set up a future burn even though it won't be what I'm carrying out, just to illustrate my point. You burn retrograde to your motion, retrograde relative to your motion, and capture your craft into orbit of the moon, into a low orbit of the moon, which takes even more fuel. So you can see it's going to take a pretty good amount of delta V to slow down from a lunar flyby to lunar orbit. And that is what this stage currently labeled 4. That's part of what it's going to do. So I look forward to doing that in my next video. But for today, we have our burn set up in 1 hour and 20 minutes to send this currently 118-ton craft to throw its payload of about 30 tons towards the moon. Let's just close. I'll leave that open, why not? All right, but yeah, so that has been the launch of the first launch of Saturn V. in-flight test of Gemini-Direct, but this time with all full tanks and everything. Everything is full of tanks so that it can actually, has a ton of delta V, so it could carry out potentially the whole mission of getting into orbit of the moon and landing on the moon and returning to Earth. Hopefully it can carry all that out, but because we have not saddled it with fragile crew, we can take some chances and see if this craft will actually work. So thanks for watching. This has been RP-0 America. Goodbye.